Okay, well, thank you very much. And again, many apologies that we have to do this remotely, but I'm sitting down here in Canberra, Australia, and we're basically isolated from the rest of the world and indeed from many other parts of Australia. So I've pretty much spent the last 6 or 7 months of my life sitting in Canberra. So hopefully by next year I'll be able to come. But with this technology, I'll be able to give you my presentation. So we're going to start talking about two major concepts that come together here. One is the Anthropocene, which we'll start off. That's the background information that we need to understand why we have this concept of planetary boundaries, what is it, and how it might guide us into the future. So let's jump into the first slide. And if you could, there we go. So the Anthropocene actually came into existence as a concept and a word in the year 2000, and it was a Dutch scientist named Paul Crutzen who was working at the Max Planck Institute of Chemistry in Germany, who first came up with this idea in the year 2000. He was working with a big international program called the International Biosphere Program, and we were having a meeting in Mexico in 2000 summarizing the first decade of our work. And when Paul was listening to all the presentations from the science, he got a bit annoyed because everyone was referring to the Holocene as the state of the Earth system we were in. And he interrupted people and said, humans are changing this planet so much that we're not in the Holocene anymore. We're in the, and then he had to think of a word. And he just blurted out the Anthropocene. And now, of course, it's an important moment in scientific history. So if we go to the next slide, then we'll see what he was talking about. This is the Holocene reference point that you can see there. So we're looking now at about 100,000 years of Earth history in terms of the global average temperature. We can get this information from ice cores. But you can see about the last 12,000 years on the right-hand side of that graph, temperature has been warmer and it's been very, very steady. This is really important for us humans because this is the period that has allowed us to develop agriculture, villages, cities, and so on. Our population has expanded, we've become wealthier, we're living longer, and so on. So it's a really, really important point in Earth history. But when Paul was listening to all the changes that are happening in the Holocene, he was saying we have left this nice, beautiful period of Earth history that has been so good for humans. So let's go to the next slide, please. So what we did then as part of the IGBP synthesis that I was coordinating was we took Paul's idea and said, well, let's go back and look at the last 250 years of human activity on the Earth, because Paul proposed that we left the Holocene about the time of the Industrial Revolution. That was the big switch in how humanity operated. So here you see 12 little graphs of what we call a human enterprise. So it's things that humans do. It's population, it's economy, it's resource use, it's communication, and so on. And each of those little graphs go from the year 1750, just before the Industrial Revolution, to the year 2000 originally. These ones I'm showing you have now been extended to 2010. And you can see they're all rising exceptionally rapidly, but it's not an even curve. You can see that the changes in the human enterprise were relatively slow and relatively small through the early part of the Industrial Revolution, all the way up until about 1950. And then humanity exploded, population, economy, resource use. And it got the nickname of the Great Acceleration in human activity. And of course, this is a very interesting phenomenon, but the question for us Earth system scientists is, what does this actually matter for the Earth system? So if we go to the next slide, you will see 12 more graphs in exactly the same style. So they start at 1750 and they go to the year 2000. But now we're looking at our home planet. We're looking at the Earth system. And the top 6 of these are what we call the geosphere, the non-living part of Earth. So you can see the greenhouse gases there. You can see climate in the middle of the second row. You can see ocean acidification and so on. And the bottom 6 are the biosphere, so the living part of Earth. You can see some indicators for how the ocean is changing, some indicators for how the land is changing, some indicators for the coastal zone, and so on. But we wanted to see, can we see any influence of this massive explosion of human activity in the Earth system? And the answer is yes. When you look at those graphs, they look remarkably similar like the first 12. So in fact, there's a good reason for that, that in each of these 12, we can say for certain that the major cause of those curves is human activity. It's not natural variability. There is a mass of scientific information that supports that statement. And the second statement we can say, in all 12 of those, we have moved outside of the Holocene. We have left our Holocene envelope of stability. So basically, these 24 graphs together are the basis, the scientific basis, the evidence basis for the Anthropocene. And again, they support the fact that it really wasn't the Industrial Revolution that was the starting point. It was the Great Acceleration that started around 1950. So let's go on to the next slide. So what we're going to do now is look at the two big parts of the Earth system, the geophysical part. I use climate change, and then a few slides later, go on to the biosphere. Well, this is a well-known graph. This shows the rise in global average surface temperature since we had reliable global measurements around 1880 or so up to the present. And you can see again from the mid-20th century a strong and accelerating rise in global temperature. It becomes more striking when you put it in a longer-term context. So on the next slide, what we do is we go back for the last 2,000 years or so, and we have good records of what temperature was doing through ice cores, through other types of proxy measurements of temperature. So what I've done is I've taken the instrumental record of the last century and a half, and I've put it on the same 2,000-year time scale. So you can see what a dramatic change this is already. These are observations. These aren't model projections. So we can see that the human influence on the climate has pushed the temperature way outside the boundaries of the last 2,000 years. And you can see that the rate at which it's rising is extraordinary from a long-term perspective. And this, of course, is why we're seeing all these impacts, why we're seeing bleaching of the Great Barrier Reef and other coral reefs, why we're seeing an increase in fires, why we're seeing an increase in coastal flooding from rising sea levels, more heat. All of this is outside the norm, outside the normal variability of the climate over the last 2,000 years, and indeed over the last 12,000 years. So if we go to the next slide, we can look at some of these rates of change. CO2 is rising at a rate that is 180 to 200 times now faster than it has in the past. The temperature is rising 170 times faster than it has in the past. So these are rates that the Earth has not seen for a long, long time. In fact, the last time we can see such a rapid rise in temperature was about 56 million years ago, well before humans were even on the planet. So these are extraordinary changes to the geosphere, to the physical part of the Earth system. So the next, we'll go to the next slide. And we can look at human transformation of the biosphere. This is what a lot of the land surface actually looks like. But we can actually make some measurements here as well to give us some numbers for how the biosphere is changing. So if you go to the next slide, you can see that there was a big assessment of the changes to the biosphere published last year by the Intergovernmental Science Policy Platform. So next slide, please. They made a number of major conclusions. Here are the three most important ones. Nature is declining globally at rates unprecedented in human history. About 1 million animal and plant species are now threatened with extinction, many in just a couple decades. The web of life on Earth is getting smaller and frayed. Next slide. This is a quite astounding fact. When you look at life on the land, terrestrial vertebrate, these are all creatures that have a backbone, mammals, birds, reptiles, amphibians. And you add up the mass, the weight of all of them. Our domesticated animals, pigs, chickens, cattle, are 67%, two-thirds of the weight of all animals on land. We humans are another 30%, just our body weight. That means that all wild creatures on land now comprise only 3% of the mass of life on the land. It's a remarkable statistic, which shows just how much we dominate the land. Next slide, please. So we've done a long-term look at what's happening to the biosphere, led by Mark Williams, working with the Anthropocene Working Group. Next slide, please. So what he's saying is that we're homogenizing flora and fauna. We're moving animals, we're moving plants around the world. We are now commandeering, using up to 40% of the net primary productivity of the planet. Every year, there's a certain amount of productivity, of growth, of plants and so on. We are now co-opting up to 40% of that. We're now directing the evolution of other species through genetic engineering. And we're interacting increasingly with the technosphere, for example, through pollution of plastics. So these, he says, are signs of a new third stage of biosphere evolution in the history of the Earth. So when you actually look at all this data from the biosphere, it's actually even more dramatic than the climate. Next slide. Well, the Anthropocene Working Group was formed in 2009 by the geologists to see if Paul Crutzon's idea actually should be added to the geological timescale. And we're going through a process now where the Anthropocene Working Group, comprised of 34 members, has now officially recommended that, yes, this is geologically real, and it should start around 1950. And you can read there a number of commissions and committees that it has to go through before it's actually formalized, and that will happen over the next few years. So we expect in the next 3 or 4 years that we may have a new epoch added to the geological timescale, which spans 4.5 billion years. The next slide. Well, we need to take an Earth system perspective if we want to understand why we need a concept of planetary boundaries, which I'll get to in just a minute. Next slide, please. What I'm going to do now is take this slide that we've seen before. This is the rise in global average temperature. Next slide. You've seen this one before. That's where we are today, the year 2020. But let's just go 80 years into the future, to 2100, and look what our future looks like. Next slide. The IPCC has used a range of climate models to project what temperature might be doing in 2100, and they're shown on this graph. The blue line down at the bottom is very low emissions. That's basically the Paris targets. We would add another degree or so to climate and maybe stabilize it too. But we're on track towards those top curves of 3 or 4 degrees by 2100. And you say, well, 3 or 4 degrees doesn't sound like very much, but we have to put this on a long time frame, an Earth system time frame, to understand how dramatic that is. So if we go to the next slide, you can see that same graph I showed you before with the spike on the end. Let's go to the next slide. And now you see what those projections for 2100 actually look like. It's an enormous spike, 3 or 4 or 5 degrees by 2100. It's about the same differences between the Ice Age and a warm period, but in the opposite direction. So it's an enormous shock to the Earth system. Many of us think that humans, our societies, even our modern technologies will not be able to cope with a climate change that big. Next slide, please. So we are committed to at least 1.5 degrees, I think probably closer to 2 degrees, even with the emissions we've already made, plus what's already in the pipeline. Next slide, please. But if we really keep emitting very much, at very high levels like we are today, we could go to 4 degrees or even above. And as I said before, this is really a challenge to our civilization, with collapse a possibility. But what I want to talk about now is the difference between a 1 and 2 degree rise and a 4 degree rise. Next slide. There you see the tipping points. Now what these are they are parts of the Earth system that can change very rapidly due to human pressure. So here you have a map, and we see they come basically in 3 types. You can see ice at the poles, the Antarctic ice sheet, Greenland, the summer sea ice over the Arctic Ocean, and so on. You can see large biomes like the Amazon rainforest and the big forest across the north, Canada and Siberia. But you can also see circulation patterns like the North Atlantic circulation, which is very important for Europe. It's also important for the Amazon and other circulation patterns. Here's the problem. These are subject to tipping at increasing rates of temperature rise. You see up in the upper left that several of them are vulnerable at even 1 degree and will likely tip between 1 and 3, more at 3 degrees and above. So the IPCC assessed these in its special report on the 1.5 degree Paris target. Next slide, please. And you see they assess a moderate risk of these large-scale singular events. That's their technical term for tipping points at 1 degree and a higher risk at 2.5 degrees of warming. So as I said before, we're already above 1 today. We're at 1.1, and it'll be very difficult to hold the temperature rise below 2. So we need to take these tipping cascades very seriously, because they are the processes which could take control of the climate system out of human control, and the system itself would shift to a much hotter state. Next slide, please. So very recently, within the last 6 months or so, a group of us have assessed where we stand with these tipping elements. So you can see them there. All of those that are labeled are actually showing signs of being activated. In other words, ice loss is accelerating from Greenland, also West Antarctica. The Arctic sea ice is shrinking. The Atlantic Ocean circulation is slowing down and has since the mid-1950s. We're getting more droughts and fires in the Amazon. Permafrost is starting to thaw. So we're already entering dangerous territory. But let me tell you why it's even more dangerous than that. These tipping points are actually linked. I'll give you an example. As the Arctic sea ice melts during the Northern Hemisphere summertime, it shrinks. And so what that does is it uncovers more dark ocean water. That absorbs more sunlight, and that accelerates the warming in the northern high latitudes. Well, that's where the Greenland ice sheet is. And as it warms even more there, that ice loss accelerates even more. So there is more fresh water being poured on the Atlantic Ocean, North Atlantic. That slows down the Atlantic circulation even more. What does that do? It decreases the rainfall in the Amazon forest. That leads to more droughts, more fires. So here we have a direct link between melting ice on the Arctic Ocean and the burning of the Amazon forest. And you can see there are other areas. These are linked. And the problem is we could get to a point where these linkages, these cascades, could become unstoppable. And that's the real concern, is that the Earth system would simply move out of our control and go to a much hotter state. So we made this statement here, very important one. If damaging tipping cascades can occur and a global tipping point cannot be ruled out, then this is an existential threat to our civilization. No amount of economic cost-benefit analysis is going to help us. Next slide, please. Right, that was the quote there. Next one. Yes, so what we did a year earlier than that work was to try to draw a little cartoon of what this might look like. So we call this a stability landscape. So you see valleys and ridges, and valleys are stable parts of the Earth system. Ridges are where the Earth is unstable. So we see ice ages on the left, that's the blue bit. We see a little warm valley in the back of the diagram. That's the Holocene back there. But we've now pushed the Earth away from the Holocene. So we're sitting here opposite the word that says Anthropocene on the right. But we've come to a fork in the road. So we can see here that if we keep going the direction we're going, we could hit what's labeled here as the planetary threshold. That is the tipping cascade that I've just talked about. So if we go over that threshold, there is no turning back. We will drop into hothouse Earth. That's the 4 or 5 degree world. It's very hot. It's not good for humans, but it's very stable. That's why it's a deep valley. We know the Earth has been there before in the deep past, and it could sit there for millions of years. But our challenge is to change the direction of where the Earth system is going toward that valley on the left called stabilized Earth. That's very important. That's the Paris climate targets. That's the stopping the degradation of the biosphere and restoring it. And this is what's required, what we call Earth system stewardship is required to reach stabilized Earth. That's our challenge. Next slide. So we need a guidance system to guide us to stabilized Earth and away from this tipping cascade. And that's where the planetary boundaries came in. They were introduced by Johan Rockström and colleagues in 2009. And we asked ourselves a very, very simple question. What are the boundaries of the most important processes on Earth that we should not transgress if we want to keep a stable Holocene-like state? That was the simple question. Actually, answering that question is far, far difficult, but we've had a go at it. Next slide, please. We published the first article in 2009. We published an update article in 2015. And so our mantra here is guiding human development on a changing planet, and our goal is maintaining the Earth system in a Holocene-like state. Next slide, please. So just quickly, where does this, next one, please. So where does this fit into our little Earth system diagram? Well, it's the guidance system we need for stabilized Earth. So getting from where we are, for that little globe in the middle of the diagram, to stabilized Earth, we need something to guide us, to monitor how we're tracking, to keep us within the limits of a stabilized Earth. And that's exactly where the planetary boundaries come in. So next slide, please. Okay, that's the planetary boundaries, yes. Okay, next one. Right, so this is what the planetary boundaries actually look like. We've written them as this now iconic sort of radar-looking diagram. As you can see, there are 9 of them. Some of them are very familiar: climate change, biosphere integrity. But we have other ones like how much land we can change, how much water we can use, how much excess nitrogen and phosphorus can we put into ecosystems. What about acidifying the ocean? What about atmospheric aerosols? Those are pollutants into the air. And of course, the ozone hole. And there's another one in the upper right there called novel entities. That's a difficult one because that is new stuff that humans are throwing into the Earth system: radionuclide, plastics, and so on. So what we did was we said we want to have a very safe zone called a safe operating space. That is the green wedges right in the middle. If we could stay inside those green wedges for all 9, we could pretty much guarantee we would be safe, we would have a stable Earth, humanity could thrive. Then there's a middle region called the zone of uncertainty, or I like to call it the zone of increasing risk. That if you push any of these boundaries out beyond the green space, you're starting to get into trouble. The outer circle is the zone of high risks. When you reach that, we know you're in trouble. And you can see that for various boundaries, some are still in the green, but we have 4 of them that are already outside the safe operating space. Climate change, already halfway up to the zone of very high risk. Biosphere integrity, way outside where we ought to be. 6th great extinction event is underway. We're eroding the stability of the biosphere at an enormous rate. Also, phosphorus, nitrogen, we're putting far too much. We're eutrophying fresh waters. We're now eutrophying the coastal zone. Land system change is also outside the boundary. We're doing an update now, and I'll just give you a preview that we're going in the wrong direction. So our 2020 assessment suggests that we will have more of these boundaries outside the safe operating zone. Next slide, please. This is an example of how complicated these are. This is a biosphere integrity planetary boundary, and it links to other ones. It's based on biodiversity and the functioning of the biosphere. But it relates to climate change, it's linked to water availability, and it has impacts for human health and indigenous cultures and so on. So when you dig into the planetary boundaries framework, there's a lot of science that goes in to determine where these boundaries actually lie. Next slide, please. We can actually map what some of them look like. So here's what the biosphere integrity planetary boundary looks like spatially. So when it's red, that's way outside the boundary. When it's yellow, it's in the zone of increasing risk. When it's green, it's in the safe operating space. And it doesn't take very long to realize that the biggest transgressor of biosphere integrity is agriculture, because you can see that the zones that are painted red on that graph are almost entirely where we grow our food supplies. So that's telling us right away that our present agricultural systems are very detrimental to the integrity of the planet as a whole. We need to really rethink how we grow our food and how we are going to feed an expanding population. Next slide. The planetary boundaries have found their way into policy in very many different ways. I'm only going to talk about a couple of them, but you get an idea here from anywhere from the OECD, the Global Energy, UNEP, Sustainable Development Solutions Network, World Economic Forum, and so on. So it's already proven to be a very valuable framework for guiding policy development that is aimed at achieving a sustainable planet. Next slide, please. You've probably seen this. These are the Sustainable Development Goals, which replaced the Millennium Development Goals. And there are 17 of them. They are designed to cover all aspects of human life. How do we achieve the social gains that we need to have to bring people out of poverty and so on, and at the same time reduce human pressure on the planet, and reach sustainable development. So interwoven in all of these are the 9 planetary boundaries. They don't sit there explicitly, but when you unpack them, they are in there guiding many of these development goals. So this is a very big opportunity for us humans. It's a chance really to change the direction in which our society is going. But the real question is, do we really need a much deeper transformation than what we're talking about today if we're going to achieve the SDGs and if we're going to live within the planetary boundaries? Next slide, please. I just want to highlight now 2 of what I think are the most innovative approaches, innovative applications of the planetary boundary framework. The first one was designed by Kate Raworth. She's an economist at Oxford University in the UK. And she said these 9 planetary boundaries are great. They provide an environmental ceiling within which humans should live on the planet. But she says we also have social issues that we need to deal with. We need to deal with equity issues. We need to bring people out of poverty and so on. So she designed this diagram called the Doughnut, with the inner circle being the social floor, what we have to do so that every human has a decent life. But at the same time, we have to ensure that we have a planet we can live on, which is the environmental ceiling. And you see there the 9 wedges, the 9 planetary boundaries. She's written a beautiful book on Doughnut economics, and she's highlighted 7 or 8 really important key issues that need to be dealt with. I've just put 3 of them here because I think they're the most important ones. We need to move away from neoliberal economic thinking, cause-effect thinking, simplistic thinking. We need to go to dynamical thinking, systems thinking, complex systems in a technical sense. We have to deal with the equity issue, and our economy should be distributive by design, not that governments have to redistribute after the economic system has skewed the benefits of the economy. And the biosphere, we need to become regenerative by design. Right now, we're exploitative by design. So those are some of the things that we need to do. Sorry, next slide, I should have said. She's put those 3 up there. You can read them now. Okay, let's go on then. And this is Kate's vision of how a corporation should run in the 21st century. So around the board, which is round and not a rectangular board, people should be discussing, government should be discussing, corporations should be discussing how we can meet this social foundation and at the same time keep within our environmental ceiling. So right now we focus on just a few things like income, jobs, energy, and so on. And the rest of this diagram suffers. So that needs to change. Next slide, please. This, I think, is the most innovative application of the planetary boundaries I've come across. The person who invented this is Paulo Magalhães from Portugal, and he's a legal expert. And he calls this the common home of humanity, a blueprint for global governance. And he uses this beautiful analogy. What if we thought of the Earth as an immense condominium? Just like a condominium in a city or an apartment block, where everyone has his own apartment, but we have a common building that we have to maintain. It's just like that on Earth. We all have our individual countries that we live in, our individual cities, but we share a common home, and that is a well-functioning planet Earth. So if we go to the next slide, please. Right, so basically this is his idea. What happens in the legal framework in terms of planet Earth? Well, if you look at the left-hand side here, what you see is the present legal architecture. It's nation states. And of course, we adopted this maybe 300 or 400 years ago with the Westphalian system. And we've added on to it. Now we have economic zones in the ocean. So we're eating into the ocean and so on. So the only bits that are left are parts of the ocean and parts of the ice, a sort of no man's land. But Paulo is saying that is the hardware. That is the physical planet Earth. What we really need to recognize legally, and we absolutely don't do it, is the software, how the Earth functions. The big circulation systems, atmospheric circulation, the ocean circulation, what the forest does, the Amazon forest, it produces oxygen for all of the Earth, and so on and so on. So this is what he calls the software, or the Earth system, as we scientists call it. the manifestation of all the processes and parts of the Earth system as a single system at the planetary level. But the problem legally is there is a vacuum. There is no legal recognition of the Earth system. It doesn't exist in humanity's legal system. That means our economy can run wild, looking at the left-hand side, exploiting parts of the physical Earth system without any regard for how our common home functions. So Paolo's innovation is to say, we need to legally recognize the Earth system as our common home. Now, you may think that's a bit wild. How are we going to recognize something intangible? But we do that all the time. Just think of copyright in a book. The physical book are the pages of the book and the ink on there. That's the physical book. But that's not its value. Its value is the intangible meaning that those symbols in the book actually represent. And we take it for granted. But we legally recognize that through copyright. So in a way, this is just doing the same thing for our Earth. We need to recognize the software, what really gives meaning for humanity, which really gives us the environment we need simply to live on Earth. So that's his innovation. Hopefully, we're getting that just started going through the UN system. Next slide, please. So these are the main points he makes in the Common Home for Humanity, is that we must legalize and respect our intangible global commons. We don't do that yet. So that really is the idea for the Common Home of Humanity, that we need to get a legal recognition and prevent this tragedy of the commons, which is occurring now. The planetary boundaries is the scientific framework that defines what a well-functioning state of the Earth system is. So this is the critical link between the legal proposal for recognizing the Earth system and the scientific community and how we can actually define a well-functioning Earth system. So that's one of the most important uses of the planetary boundaries framework. Next slide, please. So I just want to close by saying what this really means is that we shouldn't be trying to manage the Earth or the Earth system. We can't do it. It's a huge, complex system. We don't fully understand it. There are tipping points in it, non-linearities in it, and so on. But we need to respect it. We should focus on managing ourselves. We should manage our relationship to the Earth system. And that is the key feature here. So far, a lot of what we are talking about in terms of the climate challenge is trying to manage the climate system. That's nonsense. It's a big unruly system when you start pushing it with a big stick. We need to manage ourselves. So this, in a nutshell, is what the governance challenge is all about. How do we restructure our legal systems, our governance systems, our civil societies to manage ourselves, and manage ourselves in a way that respects the integrity of our home planet, our common home? Next slide, please. So I'm just going to leave you with that idea. We are in the Anthropocene. We've left the Holocene. Our common home is becoming increasingly unstable. We may be approaching points of no return with tipping elements lurking out there. And I think we're truly now, as we look up at our planet, at a fork in the road. And it's now essential that we change direction and take the right fork of the road from 2020 onwards.